Interstellar dust, despite comprising only about 1% of the mass in star-forming regions, plays a pivotal role in the chemical evolution of our universe. These micrometer-sized particles serve as powerful nanofactories that catalyze the formation of molecules ranging from the simplest hydrogen molecules to complex organic compounds, including amino acids. The composition of interstellar dust varies across different cosmic environments, but generally consists of a mixture of materials formed in stellar outflows and those processed directly in the interstellar medium. Recent analyses have revealed surprising homogeneity in the elemental composition of interstellar dust particles, containing the complete mix of cosmic elements with the exception of volatile gases. This comprehensive analysis explores the chemical composition, structure, formation mechanisms, and chemical processes associated with interstellar dust, highlighting its fundamental importance in cosmic chemistry and the evolution of molecular complexity in our universe. Interstellar dust exists throughout space, but varies in composition depending on its location and the environmental conditions. In the diffuse interstellar medium, dust consists primarily of a mixture of stardust and interstellar medium dust. The stardust components include amorphous silicates, amorphous carbon, polycyclic aromatic hydrocarbons, and graphite. These materials originate in the outflows from stars. The interstellar medium dust component mainly consists of organic refractory material, which forms through processing of simpler compounds in space. In the local diffuse interstellar medium, stardust appears to be the dominant component. The elemental composition of interstellar dust particles reveals surprising uniformity. Analysis of interstellar dust particles by the Cosmic Dust Analyzer on the Cassini space probe identified extremely rare and minuscule particles of interstellar dust containing rock-forming elements, magnesium, iron, silicon, and calcium, in average cosmic abundance. This finding was unexpected, as most scientists had anticipated finding dust populations with varying compositions that would reflect the different processes occurring in the atmospheres of dying stars. Instead, the 36 particles of interstellar origin examined showed remarkable similarity in their composition, suggesting a homogenization process occurring in interstellar space. The dust particles essentially collect the whole element mix of the cosmos, with the exception of very volatile gases. This composition differs significantly from the stellar dust found in meteorites, which typically exhibits highly individual isotope compositions. The homogenized nature of interstellar dust suggests extensive processing in the interstellar medium, erasing the original signatures of their formation sites. Inside molecular clouds, where temperatures are extremely low, the composition of dust changes as icy mantles form around the core dust particles. These mantles consist primarily of simple molecules such as water, ammonia, methanol, and carbon monoxide. The development of these icy coatings represents an important stage in dust evolution and creates sites for complex chemical reactions. Interstellar dust forms through two primary pathways: direct condensation in stellar environments and processing in the interstellar medium itself. Stardust formation has been both theoretically predicted and observationally confirmed to occur in the high-density, high-temperature environments surrounding specific types of stars. These include oxygen-rich or carbon-rich outflows from late-type giants, planetary nebulae, and possibly novae and supernovae. The formation of stardust in stellar outflows was first theoretically proposed in the 1960s by scientists including Hoyle, Wickramasinghe, and Camejo. Infrared observations in the early 1970s subsequently confirmed these predictions, providing abundant evidence for dust formation in these stellar environments. The specific type of dust formed depends largely on the chemical composition of the stellar outflow, particularly the carbon-to-oxygen ratio, which determines whether silicate-based or carbon-based dust will predominate. In contrast to stardust, certain dust components form within the interstellar medium itself. These include the icy mantles that develop on dust grains within dense, cold molecular clouds, as well as more complex organic refractory dust components found in the diffuse interstellar medium. The organic refractory component develops through transformation of the icy mantles, a process requiring ultraviolet radiation sources inside molecular clouds and radical diffusion promoted by transient heating of the mantle. The life cycle of interstellar dust involves continuous destruction and reformation processes. Dust particles encounter harsh conditions in the interstellar medium, particularly in the gigantic million-degree hot bubbles created by supernova explosions. At the edges of these bubbles, shock fronts expand at hundreds of kilometers per second, creating an energy-rich environment where most dust particles cannot survive for extended periods. Theoretical estimates suggest that interstellar dust typically survives in this environment for only a few 100 million years, with very few lucky survivors, making it intact to newly forming planetary systems. Most particles undergo destruction and subsequent reformation in molecular clouds, which are cool, dense regions of outer space. This cycle of destruction and reformation contributes to the homogenization of dust, erasing the unique signatures of their stellar origins. Interstellar winds then transport these homogenized dust particles into solar systems like our own. Interstellar dust particles typically exist as micrometer-sized grains with varying structural properties that significantly influence their behavior and interactions. One of the most important structural distinctions is between crystalline and amorphous materials. In crystalline structures, atoms arrange in regular, repeating patterns with long-range order. Amorphous materials, by contrast, lack this long-range structural order, with atoms arranged in more random configurations. This structural difference has profound implications for the optical properties of the dust, affecting how it absorbs, emits, and scatters radiation. The structural characteristics of dust grains directly influence their spectroscopic signatures, which astronomers use to identify and study these particles. For example, crystalline silicates produce sharp, well-defined spectral features, while amorphous silicates generate broader, less distinct spectral bands. These differences allow researchers to determine the relative proportions of crystalline and amorphous materials in different regions of space. The homogenization process that interstellar dust undergoes in the witch's cauldron of interstellar space affects not only its chemical composition, but also its structural properties. The constant destruction and reformation of dust in the harsh environment of interstellar space tends to favor the formation of amorphous rather than crystalline structures, as the rapid condensation processes rarely allow for the orderly arrangement of atoms necessary for crystallization. This helps explain why amorphous materials like amorphous silicates and amorphous carbon are prevalent components of interstellar dust. The size distribution of interstellar dust particles also plays a crucial role in their behavior and effects. While most interstellar dust particles have diameters in the micrometer range, there exists a significant population of smaller, nanometer-sized particles as well. This size distribution affects the dust's optical properties, surface-to-volume ratio, and susceptibility to various physical processes like radiation pressure and gas drag. Inside dense molecular clouds, where temperatures fall to just a few degrees above absolute zero and densities are relatively high, dust grains accumulate mantles of ice. These icy mantles consist primarily of simple molecules that freeze onto the grain surfaces. Water typically dominates these ice layers, with significant contributions from other molecules including ammonia, methanol, and carbon monoxide. Direct spectroscopic observations of these icy mantles provide crucial information about their composition and abundance. The formation of these mantles occurs through both direct freezing of existing gas phase molecules onto cold grain surfaces and through chemical reactions that occur on the surfaces themselves. Surface reactions are particularly important for molecules like water and methanol, which form much more efficiently on grain surfaces than through gas phase processes. As molecules accumulate on the grain surface, they form multiple layers of ice, creating a complex structure that can trap and store various chemical species. These icy mantles serve as important reservoirs of volatile elements and provide reaction sites for complex chemistry. The low temperatures in dense clouds allow volatile species to remain frozen on grain surfaces for extended periods, effectively removing them from the gas phase. This depletion of gas phase molecules, particularly carbon monoxide, has been observed toward deeply embedded protostars. Interestingly, this depletion often correlates with high abundances of methanol in the gas phase, suggesting that carbon monoxide converts into methanol on dust surfaces and is then released back into the gas through an efficient mechanism known as chemical desorption. When the icy mantles are exposed to ultraviolet radiation, either from external sources or from newly forming stars within the cloud, complex chemical processing occurs. Ultraviolet photons break chemical bonds in the ice, creating reactive fragments that can recombine to form more complex organic molecules. This processing, combined with thermal effects, transforms the simple icy mantles into more complex organic refractory material. This transformation represents a critical step in dust evolution and contributes significantly to the organic content of the interstellar medium. Interstellar dust particles function as powerful nanofactories where chemical reactions occur that would be impossible in the gas phase under the same conditions. Two primary mechanisms govern chemistry on dust surfaces: diffusive processes and non-diffusive processes. In diffusive surface reactions, reactive species undergo random walks across the dust surface, and chemical reactions occur when these species encounter each other. This process depends on the surface structure, which typically features both potential wells and intermediate barriers between them. The efficiency of diffusive reactions varies with temperature, with higher temperatures generally increasing molecular mobility and reaction rates. Experimental evidence supports the existence of diffusive surface chemistry, although precise reaction rates at the extremely low temperatures characteristic of interstellar environments remain poorly measured. An important complication in modeling surface chemistry arises from the discrete nature of dust particles. Since reactions can only occur between reactants located on the same grain, stochastic approaches become necessary to accurately model the chemistry. These approaches account for the probability of finding specific reactant pairs on individual dust grains. More recent research has identified non-diffusive processes that can significantly accelerate surface reactions. These include three-body mechanisms, where a third species facilitates the reaction between two other species. Experimental support exists for these non-diffusive mechanisms as well, suggesting they play an important role in interstellar chemistry, particularly at very low temperatures, where thermal diffusion becomes extremely slow. A particularly important process in dust surface chemistry is chemical desorption, where newly formed species are ejected into the gas phase immediately upon formation. This occurs because many reactions on dust grains release excess energy that cannot be efficiently dissipated by the grain, resulting in the ejection of the reaction product. This process provides a crucial link between solid phase and gas phase chemistry in interstellar environments. While theoretical models had predicted chemical desorption for various molecules, experimental confirmation had previously been limited to hydrogen molecules, which represent the most favorable case due to their light mass, weak binding, and the highly exothermic nature of their formation. Recent experimental work has provided the first evidence of chemical desorption for several other reactions occurring on dust analogs. These experiments revealed that chemical desorption can be remarkably efficient. For example, more than 90% of water formed through the reaction of hydroxyl and hydrogen on dust surfaces is released directly into the gas phase. This efficiency far exceeds previous estimates and suggests that chemical desorption dramatically influences the chemical composition of the interstellar medium. Interstellar dust plays a pivotal role in cosmic chemistry, serving as the primary formation site for molecular hydrogen, the most abundant molecule in the universe. In the low-density environment of interstellar space, direct gas phase formation of molecular hydrogen is extremely inefficient. Instead, hydrogen atoms adsorb onto dust grain surfaces, migrate across the surface, and react to form molecular hydrogen molecules. The exothermic nature of this reaction provides sufficient energy to eject the newly formed molecular hydrogen into the gas phase. This process represents the critical first step in the chemical evolution of interstellar clouds and subsequent star formation. Beyond hydrogen, dust grains catalyze numerous other chemical reactions that would proceed extremely slowly or not at all in the gas phase. For example, observations of deeply embedded protostars show that the depletion of carbon monoxide from the gas phase due to freezing onto dust grains corresponds with elevated gas phase concentrations of methanol. This anti-correlation demonstrates the conversion of carbon monoxide to methanol on dust surfaces and its subsequent release into the gas through chemical desorption. Similar processes likely account for the formation of many other complex organic molecules observed in interstellar environments. The impact of dust-mediated chemistry on interstellar composition can be dramatic. Chemical desorption, the process by which newly formed species on dust surfaces are directly released into the gas, can enhance certain chemical pathways by more than 10 orders of magnitude compared to gas phase reactions alone. This enormous enhancement means that even rare dust-catalyzed reactions can significantly influence the overall chemical composition of interstellar regions. The chemical influence of dust extends to oxygen chemistry as well. While molecular oxygen remains generally elusive in most interstellar environments, isolated regions with high molecular oxygen abundance have been detected, notably toward Orion. Traditionally, these elevated molecular oxygen levels have been attributed to either warm dust or shock effects. However, recent models suggest an alternative explanation: efficient formation of molecular oxygen through chemical desorption from dust surfaces. This process becomes significant only under specific conditions, potentially explaining why molecular oxygen detection remains rare and isolated. Interstellar dust also determines which chemical species remain on grain surfaces and participate in subsequent complex chemistry. The balance between retention and desorption influences the chemical evolution toward increasingly complex molecules, including those necessary for the emergence of life. The organic refractory component of interstellar dust likely contains some of the most complex organic structures found in interstellar space, possibly including precursors to biomolecules. The study of interstellar dust composition relies on multiple observational techniques, with infrared spectroscopy playing a particularly crucial role. Different dust components produce characteristic spectral features in the infrared region, allowing astronomers to identify specific materials. For example, silicate dust generates prominent features at approximately 10 and 18 micrometers, while various carbon-based components produce distinctive spectral signatures at other wavelengths. These spectroscopic observations have revealed the presence of both amorphous silicates and various carbonaceous materials in the interstellar medium. Direct sampling represents another powerful approach for studying interstellar dust. The Cassini space probe, equipped with the Cosmic Dust Analyzer, successfully captured and analyzed extremely rare particles of interstellar dust during its mission. The instrument identified 36 particles of definitive interstellar origin and determined their elemental composition. Surprisingly, these particles contained a remarkably similar mix of elements, including magnesium, iron, silicon, and calcium in average cosmic abundance. This homogeneity contradicted expectations of compositional diversity based on different stellar formation environments. Laboratory experiments with dust analogs provide essential insights into the physical and chemical processes that occur on interstellar dust. Researchers create simulated interstellar conditions by depositing reactive species onto dust analog surfaces at extremely low temperatures under vacuum conditions. These experiments have confirmed important processes like chemical desorption, where newly formed species are ejected from the surface into the gas phase. One notable finding showed that more than 90% of water molecules formed through the reaction of OH and H on dust surfaces are released directly into the gas phase, a much higher efficiency than previously assumed. Ultraviolet and visible light extinction measurements also provide valuable information about dust properties. By measuring how starlight is absorbed and scattered by intervening dust, astronomers can deduce information about dust grain sizes, compositions, and abundances. These observations have contributed significantly to our understanding of dust distribution throughout the galaxy and the relationship between dust properties and environmental conditions. Interstellar dust significantly influences numerous astrophysical processes, with far-reaching implications for star formation, planetary system development, and potentially the origins of life. As the primary heating and cooling mechanism in many interstellar environments, dust absorbs ultraviolet radiation from stars and re-emits this energy at infrared wavelengths. This process regulates cloud temperatures and affects the rate at which clouds can collapse gravitationally to form stars. Changes in dust abundance or composition can therefore alter cooling rates, impacting both the efficiency of star formation and the characteristics of the resulting stellar systems, including their masses and multiplicity. Dust opacity dominates the radiative properties of dense regions within molecular clouds, effectively determining the spectrum of embedded objects like protostars. This opacity shields cloud interiors from external radiation, allowing temperatures to drop sufficiently for ice mantles to form on grain surfaces. These icy mantles then enable complex chemical evolution, potentially leading to the formation of prebiotic molecules. Without dust shielding, ultraviolet radiation would photodissociate most complex molecules, dramatically limiting chemical complexity. The release of dust-formed molecules into the gas phase through processes like chemical desorption dramatically alters interstellar gas composition. For instance, while molecular oxygen remains generally rare in interstellar environments, isolated regions with high O2 abundance have been detected. Models suggest these elevated concentrations result from efficient O2 formation on dust grains followed by chemical desorption, but only under specific conditions of temperature and ultraviolet radiation. This example illustrates how dust-mediated chemistry creates chemical signatures that astronomers use to deduce physical conditions in distant regions of space. Dust composition and processing also connect directly to the materials that eventually form planetary systems. The homogenized interstellar dust, carried by interstellar winds into forming solar systems, contributes raw materials for planet formation. Understanding dust composition, therefore, provides insights into the initial inventory of elements and compounds available for planet building. Additionally, the organic components formed through dust surface chemistry likely contributed to the organic material inventory of early Earth and other potentially habitable worlds, possibly playing a role in the emergence of life. Interstellar dust, despite constituting only about 1% of the mass in star-forming regions, plays a crucial role in cosmic chemical evolution. Its composition reflects a complex history of formation in stellar outflows, destruction in the harsh interstellar environment, and reformation in molecular clouds. The primary components include stardust and interstellar medium dust. In cold, dense molecular clouds, these core components accumulate mantles of ice dominated by water, ammonia, methanol, and carbon monoxide. The structural properties of interstellar dust, particularly the distinction between crystalline and amorphous materials, significantly influence its optical characteristics and spectroscopic signatures. The predominance of amorphous structures results from the rapid condensation processes in interstellar space, which rarely allow for the orderly atomic arrangements necessary for crystallization. These structural features directly impact how dust interacts with radiation, affecting processes from cloud heating and cooling to the opacity of star-forming regions. Chemical processes on dust surfaces dramatically enhance cosmic chemistry, enabling reactions that would proceed extremely slowly or not at all in the gas phase. Diffusive surface chemistry occurs when reactive species migrate across grain surfaces and encounter each other, while non-diffusive processes can further accelerate reactions. The chemical desorption process, where newly formed species are ejected directly into the gas phase due to reaction exothermicity, creates a crucial link between solid phase and gas phase chemistry. Recent experimental evidence shows this process operates with surprisingly high efficiency for various reactions, potentially dominating over gas phase chemistry by more than 10 orders of magnitude. The study of interstellar dust composition combines multiple observational approaches, including infrared spectroscopy, direct sampling by space probes, laboratory experiments with dust analogs, and extinction measurements. These investigations have revealed surprising homogeneity in interstellar dust particles, suggesting extensive processing in the cosmic witch's cauldron that erases signatures of their diverse stellar origins. This homogenized dust, carried by interstellar winds into forming solar systems, contributes raw materials for planet formation and potentially prebiotic chemistry.